Funding for this program is provided by Annenberg Lerner.
Hi, I'm Pardis Sabeti, and this is Against All Odds, where we make statistics count. Scatter plots are a great way to visualize the relationship between two variables, such as ocean temperatures and coral reef growth. As temps go up, new growth goes down. Or between femur bone length and overall height, as seen in this clip from Bones, Fox's show about a forensics team.
A lot of jewelry, male. Thigh bone suggests he was tall. A D bracelet.
Forensic anthropologists know from years of collecting data that there's a relationship between the length of your thigh bone and your total height.
That makes a difference?
Facts of life, Bones.
In this case, the femur length is what influences the total height. Remember that the explanatory variable, femur bone length, goes on the x-axis, and the response variable, total height, goes on the y-axis. The data points appear to fall pretty much along a straight line. Longer thigh bones and taller heights look like they go together in a linear relationship. Statisticians call the line that describes how the response variable changes with the explanatory variable a regression line. Any straight line can be described by the equation y equals a plus bx. A is the y-intercept, the spot where the line hits the y-axis, where x equals 0. B is the slope of the line, how much y changes when x goes up by 1. X and y are the data points you're plotting, in this case, the bone and height measurements. Sizing up the data points, we can just eyeball where the line should fall. But there's a statistical technique to figure out how best to fit a line to the data. Once we have that line, we can use it to make predictions. That's how Brennan on Bones can estimate an unidentified crime victim's height even when she has an incomplete or damaged skeleton, just using the thigh bone measurement.
Approximately 6'7", right-handed.
6'7".
This man was dead for several hours before the train hit him.
The Colorado Climate Center uses regression lines in a less sinister scenario to forecast the state's seasonal water supply. Farmers, city planners, businesses, it's important to all of them to know how much water is going to be available each year, so they can plan accordingly.
The sooner you know that, the better you can strategize for planting crops, for managing landscapes, golf courses, for knowing what water can be stored in reservoirs, for understanding what water will be available to meet the interstate compacts on the various rivers. The big question is, how can we predict the water supply we're going to have as far ahead of time as possible?
Most of Colorado's water comes from melting mountain snows in the spring. So climatologists have developed a model based on two types of data: the amount of winter snowpack in the high elevations and the resulting volume of water that flows out of the mountains throughout the summer.
And what you really like is to have many years of that in the past so that you can see how the snow water content in the mountains over time has related to the amount of water flowing down the river during the late spring and summer.
So Colorado's Natural Resources Conservation Service heads into the Rockies to collect that data.
They've got hundreds of sites in the Colorado mountains, and they monitor those on a monthly basis. They do that by identifying sites that they return to year after year after year. And they collect a minimum of 10 depth and quantity subsections on the snowpack, and then they average those to come up with the total for that particular area.
So that's one part of the model, the water that's stored as snow all winter long. The second set of data that climatologists need is how much water actually ends up running downstream.
The U.S. Geological Survey operates a network of about 300 gauging stations in Colorado. At each one of those locations, we have a recording device that continuously logs the height of the river, and then we come up with a continuous record of discharge at each one of these 300 sites.
Let's graph these data points on a scatter plot. You can see that in the years when our explanatory variable, the snowpack, was high, the spring runoff, our response variable, was too. It looks like a pretty strong, positive, linear relationship. Of course, in the real world, all data points don't fall on an exact, precise line. So we need a technique to figure out the regression line that minimizes the vertical distances of our data points from the line. Let's zoom in on just these 3 points from our Colorado water data. We want to find the best fitting line with the most points as close as possible to it. This vertical distance of a point from a line is called a residual. As we shift the line, some residuals get smaller while others get larger. They can't all be small at the same time, so we need to find that sweet spot where we've gotten them as a group as small as we can. Statisticians use a method called least squares to do that. Since some of the residuals are positive, above the line, and some are negative, below the line, we square them, which makes them all positive. If you add up the squared residuals, the bigger the sum, the more the line misses the points. So we want to make that sum as small as possible. Software can do the math for you and come up with the equation y hat equals a plus bx to describe our line. We say y hat to emphasize that we're talking about the predicted value of y, not a measured value from our data set. Now we have our regression line and can use it to make predictions. Remember, the plotted points are our actual data, and the regression line predicts the y value for any x. Back to the Colorado water data. Statistical software gives us the equation for the regression line. The slope of 1941 predicts that for every 1-inch increase in snowpack, the runoff increases by 1,941 acre-feet. The y-intercept is negative 7,920, which would seem to say that if the snowpack was 0, the runoff would be around negative 8,000 acre-feet. Obviously, that doesn't make sense, and it's a good reminder that you can't extrapolate from the regression line too far outside the range of the observed data. Keeping that limitation in mind, though, the regression line can be very useful for Colorado water users.
We have found that it really does predict the amount of stream flow that we're going to have months in advance.
If you know that this winter, the Rockies saw 30 inches of snowpack, you can look at the line to predict how much water is going to flow into the system in the spring. Here's the spot on the line, and plugging in the numbers to the line's equation gives us a forecast of 50,310 acre-feet of meltwater. That's a number that can help water resource managers plan for the year ahead. The regression line works well to predict the Colorado water supply because the relationship between snowpack and river flow is linear. If the relationship you're trying to describe actually has a curve pattern, a straight regression line won't be a good fit to the data. For instance, check out this scatter plot showing the curve relationship between an alligator's length and weight. Trying to use a regression line in a case like this won't make the most accurate predictions. One way to assess how well a regression line fits the data is to make a residual plot. That's a scatter plot of all the residuals against the explanatory variable. It's as if you turn the regression line horizontal. If the dots in the residual plot appear randomly scattered with no strong pattern, like they do in the Colorado water case, both above and below the line, then the regression line has nicely captured the pattern in the data, and a linear model is a good choice to describe it. But if the residual plot looks at all curved, like in the case of our alligators, then the data pattern is curved and the linear model is the wrong one to use. Probably best to steer clear of those alligators, especially if they're hungry. You wouldn't want to become a meal that would add to their weight, no matter what the relationship to their length. For Against All Odds, I'm Pardis Sabeti. See you next time.
Funding for this program is provided by Annenberg Lerner. For information about this and other Annenberg Lerner programs, call 1-800-LEARNER and visit us at www.lerner.org.